Hello students, in this class we will discuss about the last topic in the fourth unit, that is sinusoidal modulation. So before that sinusoidal modulation, first we have to understand about the modulation. So here we are discussing about the voltage source inverters. So in that voltage source inverter, the output wave can be converted our required form, depends on the application. For that we are using the pulse width modulation. Pulse width modulation. Pulse means simply it is the pulse. It may be called as a pulse. Pulse means we have a particular time period and particular magnitude. It's look like a step. This is called a pulse. This width can be modulation. Modulation means varying. Simply modulation is nothing but variation by changing or the controlling. This pulse width modulation means the getting output can be converted into the pulse width. Modulated depends on the application. By using this technique, we can control the output of the voltage source inverter. Pulse width modulation. Look at here. For example, we are getting the output voltage V0, that V0 having a positive magnitude up to 5 time period. From 5 to 25 time period, it having minus magnitude, negative magnitude. If we are converting by using the pulse width modulation technique, we can convert like this. This pulse width will be decreased and this pulse width will be decreased. The size of the pulse width equal to 2D. Just assume that 2D, like that. We are converting this direct to waveform like pulses. This is the one pulse and this is the one pulse. This pulse may be positive pulse, this pulse may be negative pulse, like that. So why we are converting this voltage into the pulse widths will be discussed here. So look at here. The output of voltage source inverter can be effectively controlled by, so our voltage source by, what is the application of voltage source inverter? Simply which converts DC voltage into the AC voltage. So this output can be effectively controlled. We can control this output by the internal switching times, by using the internal switching times. That means we have the switches can be controlled. So in order to control this width, again we have to use the switches only. In the voltage source inverter, to convert the DC to AC, we are using the switches. That's why by using the switching time within the circuit is known as the pulse width modulation control. This name is the pulse width modulation control. Simple thing, we have a output of the voltage source inverter. By using the pulse width modulation technique, we can convert this like two pulses, one pulse and one pulse. Pulse means it's look like a step. Right. What is the requirement of this pulse width modulation control? That's why this is the objective. First, to control the RMS value of the output voltage. So generally we have two types of voltage. One is average and another one is the RMS. But RMS is our required voltage. That is the effective value. We are always calculating AC magnitudes in the RMS only. That's why we can control the RMS output voltage. By controlling the RMS output voltage means the magnitude is in our control. We can increase the magnitude or we can decrease the magnitude. That's why this is important thing. Second point, to eliminate the lower order harmonics to possible extent. That means we can eliminate the lower order harmonics. What is harmonic? The unwanted frequencies is known as the harmonics. We already discussed about this. So we have more number of harmonics. Generally, lower order harmonics means 3, 5, 7, like that. Higher order harmonics means from 11, 13, 17, 19, like this. But lower order harmonic is having a high magnitude. That's why we have to remove this high magnitude. But this high magnitude, this is the lower. Why it is called as a lower? It have low values. 3, 5, 7 is low values compared with the 11, 13, 17, like that. So these are the higher order harmonics. But the higher order harmonics have low magnitude. Low magnitude. That's why always we have to prefer to eliminate the first higher order harmonics because they high magnitude characteristics. That's why to eliminate the lower order harmonics to the possible extent. That means so our possibility depends on the possibility we can remove the lower order harmonics. Example, the harmonics are 3, 5, 7, etc. That's why we are using the pulse width modulation technique. A simple thing, from that voltage, whenever we are converting this voltage, so we are using the voltage source inverter to convert DC voltage to AC voltage. It is having the combination of, for example, we have output voltage V01 and again we have third harmonic, fifth harmonic, all composition. So in our requirement thing is V01 is our required thing. But to remove these harmonics and to control this output, fundamental output, we are using this pulse width modulation technique. We are using the pulse width modulation technique. Understand? To control the output voltage as well as the harmonics. We are using the pulse width modulation technique. It's look like this. It's a look like this. Next. And the another topic is single pulse width modulation. Simple. Single pulse width modulation means if the output having single pulse for half cycle, then the method is known as the single pulse width modulation. So name itself. For example, the previous waveform. Look at this waveform. This is the half. This is the actually this waveform is this is the total waveform. This is the complete one cycle. It has complete T period. It has time period means after that it again repeat like this. Again it is repeated like this and extended like this. You know this. So in that half cycle means this part is half cycle. This part is the full cycle. So simple thing, if the output having single pulse for half cycle, look at here. This is the output. After the pulse width modulation, we have only the single pulse. Look at here. For half cycle, this is the only single pulse. Like that. Then the method of control is known as single pulse width modulation. Name itself it represents. For each and every half cycle, it consists of the only single pulse. Then it is known as the single pulse width modulation. Simple. If, for example, just take it, consider as n d equal to 5. n means just take it, this complete value is nd. Just assume nd equal to 5. Just take it simply. And from that we can write the from this d equal to 5 by n. N is multiplied here, that's why divided here. Just multiply with 2, then 2d equal to 2 5 by n. 2d equal to 2 5 by 1. This formula is very much useful to do the removing the harmonics. Look at here. To eliminate the nth harmonic, we have to remove the nth harmonic. The pulse width value, we have to consider the pulse width value is 2d equal to 5 by n. Simply 5 by. To remove the any harmonic, we have to remove the third harmonic. Then 5 by 3. Fifth harmonic 5 by 3, like that. To eliminate the nth harmonic, any type of harmonic, pulse width value equal to 2d equal to 5 by n. This is the formula. This is very important formula. 2d equal to 5 by n. 2d means here pulse width. Don't confuse. 2d means simply pulse width. Just take it as pulse width. Understand? Right. Here, for example, to eliminate the third harmonic, pulse width value equal to 2D equal to, here what is n value? To eliminate the third harmonic means n value is the 3. Then write 5 by 3. 5 by 3 equal to, then 5 by 3 means here, this is the formula 2 5 by n, not n by n. For example, here 2 5 by 3. What is 2 5? Not n. 2 into 5 by 3. 2 5 means 360. 360 by 3 means 120. 120. Next, to eliminate the fifth harmonic, pulse width value is same. Here missing the 2, just put 2 here. This is wrong actually. This is the formula is 2 5 by n. 2 5 by n. It's a mistaken. So that's why right here 2 5 by 5. 2 5 means 360 by 5. This is 72 times. So the pulse width must be 720 degrees. Understand? So to eliminate the third harmonic, generally pulse width is 180 here because 0 to 5. But in order to remove the third harmonic, this width will become 120 degrees. And to remove the fifth harmonic, the pulse width will become only 72, like that. So by using the pulse width modulation, we can remove the harmonics. Understand? This is very, very important. The formula is to eliminate, once again I will write here, to eliminate nth harmonic pulse width value are equal, that is 2D, we can write 2 5 by n. 2 5 by n. Right. So this is for single pulse. If more number of pulses, so in order to increase the pulses, that means we up to now we discussed about the single pulse per half cycle. But here, if more number of pulses per cycle are used, it is possible to eliminate the multiple lower order harmonics. Understand? For single pulse, we are using single harmonic. If we are using the multiple pulses, then multiple lower order harmonics. Right here, if we are using the single pulse only, we will removing one lower order harmonic only. Lower order harmonic only we can remove. But if we are using multiple pulses, then we can more number of multiple lower order harmonics. We can remove multiple lower order harmonics. Understand? Right. But switches need to operate the switching frequency. So for that we have to use particular switching frequency. Otherwise, the complete system will be disabled. But we have to maintain, for this the most important thing is switching frequency. That means switching time. At which time we have to on the switch and which time we have to off the time. For that, it will increase the higher order harmonics. In this process, whenever we are focusing on the lower order harmonics, but there is a chance of increasing the higher order harmonics. In this process, higher order harmonics will be increases. Higher order means so 11, 13, like that. But they can be eliminated smaller size of filter. But we can remove this, we can eliminate this smaller size of filter. By using the small size of filter, we can remove the higher order harmonics. But lower order harmonics are very dangerous and dominate in the circuit. But lower order harmonics we can simply using the smaller size of filter, then it will be removed. That means the smaller size of filter means in the circuits we are using the capacitive filters and inductive filter. These are the filters generally we are using to remove the harmonics. Understand? So multiple, by using the single pulse we are using the single to remove the single lower order harmonic. Multiple pulses we have to use the multiple lower order harmonics can be removed, but switching frequency increases. Whenever the switching frequency increases, automatically higher order harmonics will be increases. Then these are eliminated by the filter circuit. Small filters we can use. Understand? Small filters we can use. Right. So in this we have now up to now we discussed about the single pulse and multiple pulse. So in this multiple pulse, sinusoidal pulse with modulation is one of the important technique. Sinusoidal pulse with modulation. That means we are converting this, we are converting the sinusoidal wave. We have some sinusoidal wave. By that we can convert this into pulses simply. In the form of pulses we are using. Understand? We have the input is sinusoidal waveform. That input can be converted as the output as pulses. Then this process is known as the sinusoidal pulse with modulation. Simply sinusoidal, we have the input is sinusoidal, but the sinusoidal is converted as pulses. Then that is known as sinusoidal pulse with modulation. So in order to do sinusoidal pulse with modulation, our requirement is we require a comparator circuit. Comparator circuit means it compares the inputs. It will compare the inputs, and after the comparing that it will generate the pulses. By that pulses, switch will be operated. This symbol is the switch. Symbol is the switch. By giving the number of pulses, the switches will be operates. Right. Here, what is reference wave? Simply, reference wave means our sinusoidal wave. Sinusoidal wave, name it as the reference wave. And carrier wave means we have to use a wave to generate the pulses. Here, what is the carrier wave we are using? Carrier wave is the triangular wave. So by using this sinusoidal wave as reference wave, nothing but sinusoidal wave is input, and by using the triangular wave, by using these two waves, comparator will take these two waves and it generate the pulses. That pulses will operate as the switches. So you will observe here. Just look at here. This is the sinusoidal waveform, starting from here and ending from here. This is sinusoidal waveform. This is the positive side. This is a sinusoidal waveform. So this name is the, look at here, reference signal. This name is the reference signal. And we have to use the carrier wave is the triangular wave. Look at this. This is the triangular wave. It looks like a triangle and stop some point and then will be straight line. Again it will be like this. Right. These two, so that's why this VC means carrier. VC means carrier voltage wave. Next, VR means reference voltage. Look at it. Yes. So if you observe here, wherever the reference voltage, reference magnitude is more, just that line will be shaded. Look at here. So wherever the magnitude of the reference voltage is more than the carrier voltage. Look at here. Yes. So reference voltage magnitude is this area, reference magnitude is dominated than the carrier, and this area also it will be dominated. This area also. Look at this area. This area, reference wave, carrier wave is dominated more than the reference, and shade that area. Just simply shaded that area. This is for positive cycle and this is for the negative cycle. And the generated pulses will be represented VDC. So just draw the voltage lines, just draw the straight lines. So we have some width here, just draw a pulse. Look at it. And between these 2 points, just draw a pulse. And between these 2 points, draw a pulse. Same, a pulse, a pulse, a pulse. This is the positive side, that's why we will get positive pulses. Look at here. This is the positive pulses. And this is the negative side, that's why we will get the negative pulses. Understand? We'll get the negative pulses. Look at here. Look, this is the half wave, but we have the multiple pulses. For half wave, we will get the multiple pulses. We'll get the multiple pulses. Understand? So that's why this is multiple pulses wave. Understand? So this is the converting this sinusoidal waveform into the pulses. This procedure is known as the sinusoidal pulse width modulation. Sinusoidal pulse width modulation. Look at here. Sinusoidal pulse width modulation. And we can take other way. That way is it start from here and end from here. And here straight line and end from here. But we are considering the same triangle, but this triangle is start from 0, but here start from maximum. Start from 0 and take the three triangular waves, and both will be this sinusoidal waveform and this triangular waveform is again after the half cycle it will be touched at one point. After that negative side also we have 3 waves and touch ending with this point. But here this 0 point and maximum point will get at starting and ending, both are getting 0, and ending of the sinusoidal wave both are different. So that means we are using some different form of triangular wave. Then we will look at here. Same procedure here, wherever the reference wave is magnitude is more than between these 2 points, we will get the pulse here. Here also between 2 points we will get the pulse. Between 2 points we will get the pulse, but we will not get pulse anymore here. Here also we will get the pulse here. So this is the way to generate the pulses. This is the way to generate the pulses. Understand? This sinusoidal waveform is converted into pulses known as the sinusoidal pulse width modulation. In this reference wave is nothing but the sinusoidal wave. Carrier wave is nothing but the triangular wave. Triangular wave. And we will discuss some more points regarding this. In this, just first reference wave frequency, for example, FR. So reference, what is reference wave here? Just draw a simple waveforms. Generally reference wave is the sinusoidal wave actually. So just take the, name it as the reference wave or VR, right? Here, for example, this frequency is assumed that FR. Understand? FR. And the time period equal 1 by FR. Why? The relation between time period and the frequency is 1 by F. 1 by F. Right. Reference wave time period for half cycle. For example, this is for complete time period. This is for the complete time period. For example, if it is for the half cycle only, half cycle, it become half. That's why 1 by 2 FR. This is the 1 point. Reference wave frequency per half cycle equal 1 by 2 FR. This is the first equation. This is the first equation. Understand? Simply, reference have the frequency VR, but time period equal to 1 by FR. But reference time period for half cycle 1 by 2 FR. Right. Next, carrier wave frequency equal FC. What is carrier wave? Carrier wave is look like this. This is the triangular wave. This is the carrier wave time period. Yeah. The carrier wave frequency equal to Fc, for example. And the carrier wave time period, complete time period equal to 1 by Fc. Simple reason. The relation between time period and frequency equal to T equal to 1 by F. Right. Here, number of pulses per half cycle. So here, if you observe here, in this, by looking directly, we will get we have 3 pulses per half cycle, 3 pulses per half cycle. But here we only 2 pulses per half cycle and 2 pulses per half cycle. Like that. So in order to find out the number of pulses per half cycle, the formula is reference wave time period per half cycle by carrier wave time period. So by using this, we will get the number of pulses per half cycle. Number of pulses per half cycle. Generally, reference wave time period for half cycle value is 1 by 2 Fr. 1 by 2 Fr by carrier wave time period equal to 1 by Fc. 1 by Fc. By doing the calculation, Fc by 2 Fr. Fc is carrier wave frequency. Fr is reference wave frequency. Reference wave is nothing but the input wave. Carrier wave is which is a supporting wave to generate the pulses. Here, number of pulses per half cycle equal to Fc by 2 Fr. Fc by 2 Fr. Understand? Fc by 2 Fr. This is very important formula. It is useful to do the more problems regarding this. It will be useful to do the problems. That is, number of pulses per half cycle equal to Fc by 2 Fr. Okay, right. Next, in this we have another important parameter, that is the modulation index. Modulation index means a parameter. We can simply say modulation means it is useful in pulse width modulation. So pulse width modulation. So from this, modulation will be taken and a index will be considered, then modulation index. So here, modulation index, the ratio of the reference voltage to carrier voltage is known as the modulation index. Understand? Look at here, the ratio of the reference voltage. We have reference voltage, that is input voltage. Carrier voltage is nothing but simply supporting voltage. Understand? Input voltage to supporting voltage is known as the modulation index, simply. And look at here, just look at here. So for reference voltage, we have a voltage, that is VR, and for carrier voltage we have some magnitude voltage, that is Vc. The modulation index equal to VR by Vc. Right. If modulation index is less than 1, it is known as the under modulation. Simply. So if the by doing this calculation, we will get if less than 1, then it is called as the under modulation. If modulation index is greater than 1, it is known as the over modulation. Then it is known as the over modulation. Right? If it is less than 1, under modulation. If it is more than 1, over modulation. But we have two modulations which is preferred. We will discuss in the next point. That is, under modulation is preferable. That is, under modulation is preferable always. This is very important point. Under modulation is preferable. If modulation index is less than 1, then pulse width modulation have 2n plus or minus 1 harmonics. It will generate the 2n plus or minus 1 harmonics as lower order harmonics. As lower order harmonics, it will generate this amount of 2n plus or minus 1 lower order harmonics will be generated here. That's why this is preferred. But compare with in the over modulation, we will get the more number of harmonics. It is only less number of harmonics. Understand? Where n is the number of pulses per half cycle. Where n is the number of pulses per half cycle. For example, we have two pulses We have two pulses, then the harmonics is 2 into 2 plus or minus 1. That means 4 plus or minus 1. 4 minus 1 we will get the 3, 4 plus 1 we will get the 5. 3, 5, 2 harmonics will be eliminated. Third harmonic and fifth harmonic, 2 are eliminated. Okay, na? That's why lower order harmonics are eliminated. That's why it is important. That's why these 3 and 5 harmonics are eliminated. Harmonics are eliminated. For example, if we have the 4 is there, then number of pulses is 4, then will be 2 into 4 plus or minus 1. That's 7 or 9. Harmonics are eliminated like that. So the important thing is the modulation index. It is the ratio of reference magnitude to carrier magnitude. And always modulation index less than 1. That is named as under modulation. That is very efficient thing. Okay. So this is about the modulation index. Next, we will discuss a problem regarding this sinusoidal modulation. So the problem is a modulating signal m of t equal 10 cos 2 pi 10 power 3 into t is amplitude modulated with a carrier signal c of t 50 cos 2 pi 10 power 5 t. Find the modulation index and number of cycles per half cycle. Not cycles, this is actually number of pulses. This is number of pulses, right? So solution, first given data, modulating signal. He mentioned the first thing is the modulating signal, that is represents with m of t. That value is 10 cos 2 phi into 10 power 3. Amplitude is modulated a carrier signal. We have a carrier signal. It is represents with c of t. That is 50 cos 2 phi into 10 power pi t. So carrier signal, he directly mentioned this modulating signal means the signal which is modulated, which can be divided into the pulses, is nothing but the modulated signal. Or the another name is reference wave. The another name is the reference signal. No problem. Right. Find the first question is find the modulation index. Right. What is the formula for modulation index? Modulation index means magnitude of the reference voltage to magnitude of the carrier voltage. So compare with general form. This form is Vm cos omega t. This is also compare with this Vm cos omega t, like that. Yes. From this reference signal magnitude is 10 and carrier signal magnitude is 5. Understand? So we will get 0.2. So by that we will get modulation index value is the 0.2. What is next? Next is number of cycles per halves, number of pulses per half cycle. What is the formula for the number of pulses per half cycle? That is Fc by 2Fr. Fc by 2Fr. Understand? Right. Here Fc means carrier wave, but what is F? Look at here. This is 2 phi 10 power, compare with this omega, compare with this omega. So first, for modulate, we have two signals as well as carrier. For modulating signal, just compare with omega equal to, what is omega value equal? 2 phi into 10 power 3. But what is 2 phi? 2 phi means 2 phi f equal to 2 phi 10 power 3. What is f equal to here? 10 power 3. Modulating a reference signal equal to 10 power 3. Next here, omega equal to, for carrier signal it is 10 power 5. 2 phi into f equal to 2 phi into 10 power 5. Here f carrier signal equal to 10 power 5. So from that, just fc value equal to 10 power 5 and 2 into reference value equal to 10 power 3. Understand? These 2 times will cancel and remaining is 10 power 2 by 2. So 10 power 2 means 100 by 2. This is 50. 50 cycles. Okay. So that's why number of cycles, pulses per half cycle equal to 50. So in this modulating method, by using this modulating signal m of t and the carrier signal c of t, we will get the modulation index as 0.2 and number of pulses per half cycle is 50. So this is the method to do the problem like this. You can ask in these two type of formulas. Okay. So this class is about the sinusoidal modulation. Okay. Thank you.